This tutorial solves diffusion equation in one dimension with a source, and it's related to the previous problem that we did where there was no source. And so now we have the same situation. We have a rod that has been sitting on ice for a long time, so it has temperature has reached 0, and then we place a source, could be a candle or some electrical coil around that rod at that point that is heating it. And so this heat is 10 units per second. So that's at the rate at which we are putting it into the rod, and we are putting it at 7 meters from the left side. So this is 3 meters and 7 meters. So the question is, if we leave this here for 5 seconds, what is the behavior of temperature of this rod? And previously we had no source, so if we include the source in the previous equation, we will have a source term also included in our update equation. And it's the same idea extended, where our new temperature is equal to the previous temperature plus some update because of the diffusion itself, and then plus another update because of the source. And so both of these contribute to the change in the temperature. And how are we going to define this Q dot? That Q dot is defined as that it has a value of 10 for time 0 to 5 seconds and 0 after that. And so what we have to do is just take our original code that we had in the previous problem, and let's save as, we can save it as diffusion 1D with source. And first of all, our initial condition has changed, so this has reached 0 degrees Celsius. So when we get to this point, we will change it to 0 degrees Celsius. And then when we come to the main loop where the new temperature is being calculated, we need to add something here at one location, which is location number where the length is 7 meters from the left. So where is that index? If we look at our indices, the x goes from 0 to 10, and the 7 meter index is about here. And we can actually calculate, just count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's the 15th index. But we can actually do a better job than just every time trying to count it. We can right here say source term. So the first part is the location of the source. So let's say Sx is the source x coordinate. This will be rounded value of the 7 times nx over lx. So this is basically location of source. And if you calculate this, you will see that it actually gives you 15, but you won't have to count every time. It actually depends upon, and this is simple ratio. We're just ratioing to find what's the index of the Sx. And the reason I'm rounding it, because this ratio is most likely going to give a decimal point, but all of our indices are integer values, so we convert this into an integer. And the next part is we need to tell it the source. So Tn at this location, which is the 15th index, is equal to whatever we have already calculated there plus a source term. And what is the source term? Well, the source term is delta T times the 10 divided by the rho and Cp. So let's say dt times 10 divided by rho divided by Cp. So that's our source update. Now we have to keep in mind that this is only when t is less than 5. So this only applies when t is less than 5, otherwise it doesn't apply. So now we have updated all of our information here, and First, let's run it for the Dirichlet boundary conditions. And once we run it, we can see how there is heating going on and then cooling going on. Let's increase this source, heat of source, by 100, and then let's see what happens. So we have increased the amount of heating by 10 times. So as you can see, there's heating going on at location 7, and then after 5 seconds it starts to cool down. Now we can do the same thing by changing the boundary condition. So let's change the boundary condition to Neumann boundary condition and rerun the code. So now on this side we have insulation. So the heat is still flowing this way because of this higher temperature, but after that it starts to cool down over the whole rod. So you can see how this implementation where we take the diffusion equation for this problem, we discretize it using finite difference method, and then using our initial and boundary conditions, we can learn how the temperature is changing along this rod. So if you need to increase the resolution of this problem, you can always increase the number of points over which you want to calculate. Let's say we increase it to 51, and if you run it, you will see that the time scale has changed. So now our time is incrementing at a very small scale, and so this sort of determines how our time is going to change. So this only ran for 10 seconds. This CFL condition is that determines what the corresponding time is for the Courant number that we have set up. This concludes the tutorial.